Good morning, Dr. Arsrina, and welcome to our presentation. I am Munirah binti Rahidin, and I'll be presenting regarding the research journal, which is Enhanced Furfural Production in Deep Acidic Solvent Compromising Alkali Metal Halides as the Additive. So in this research journal, we are going to study the effect of those alkali metal halides that act as the additive in deep acidic solvent for the furfural productions. And then furfural production is really important as it has been widely used for different purposes like making inks, plastic, antacid, fertilizer, and more. They even serve as the building block for the transportation fuels like the methyl furan. So most processes of furfural production are carried out in aqueous media by using homogeneous acidic catalysts like sulfuric acid and hydrochloric acid. And then heterogeneous catalyst was used by aluminium sulfate. So source of furfural can be obtained by agricultural waste like sugar cane bagasse and corn cobs. And furfural production is through the dehydration of pentose sugar like xylose and arabinose, and then or removing water molecule from the 5-carbon sugars. Three objectives was found in this research journal, which are firstly to study the effect of addition alkali metal halide to acidic deep acidic solvent in the production of furfural, and even to determine the most effective way of boosting xylene conversion into furfural, and lastly to discover alternative methods in producing renewable sources. And then these are all the metal halides has been used in this research for the yield of furfural to the dehydration of xylose. These are the methodology. The mixture was used of both solvent and catalyst. Temperature was carried out at 150 degree and 130 degrees Celsius. A response surface methodology was applied, which is used to optimize and promoting high furfural yield. The qualification was carried out by HPLC.
The results are divided into three parts. First, the metal halide selection and screening, and these are the salts that we use. At high temperature, which is 150 degrees C, as in figure 1, we can see addition of sodium bromide shows the highest furfural yield, about 92.8% when compared to other salts. And the trend of the salt ion is not of our main focus, but generally, an ion will interact with polonium ion while cation interact with chloride ion. At lower temperature, which is 130 degrees C, addition of lithium chloride gives highest furfural yield. In terms of salt ion effect, lithium plus has good activity, so that cation effect is much more crucial rather than the halide and ion. So let's compare between the addition of sodium bromide and lithium bromide at certain parameters. Lithium bromide is used because we want to see the behavior of the different metal in metal halides, and therefore we choose the same halide and ions. Blue frame shows that lithium bromide outperforms the reaction at lower temperature and continuously increase to maximum at 1.5 minutes in the red frame. In purple frame, it decreases when reaction time gets longer because the furfural yield begins to decrease, and also there is side product form. When the temperature gets higher and reaction occurs longer, the yield production when sodium bromide is used increases to the max. After screening, we optimize the reaction by using response surface methodology (RSM). The parameters are time, temperature, and concentration of lithium bromide. Lithium bromide is used because it works at lower temperature and has faster reaction time. We use ANOVA to estimate the influence of some variables on the furfural yield, so maximum furfural yield is obtained at these preliminary assays. So to conclude, the optimal values are as shown in slides. The expected yield is 92.2%, close to the previous data. However, 89.5% furfural yield obtained experimentally. Next, I will pass to Izzati to discuss on the third part.
So now I will continue on the furfural, reaction media and catalyst recovery and reuse. The final step of this work focused on the recovery of pure furfural from the reaction media and the recovery and reuse of the reaction media with the dissolved salt. The recovery of furfural was achieved through the direct distillation of this compound from the reaction media by reduced pressure distillation in the conditions of 50 degrees Celsius and SiC and bar. The result from these strategies are 85.9% of furfural can be recovered, and the obtained furfural is of high purity level, which can be proved by NMR spectra and HPLC chromatogram. So, with this strategy, it was possible to recycle the dibutyltic solvent up to 3 times as represented in Figure 6. From Figure 6, it shows a decrease in yield was observed in the first recycle due to the accumulation of insoluble sites products, humins in the reaction media. However, this yield is maintained throughout the next cycles. The integrity of deep butyric solvent attained in the last cycle was confirmed by comparison with freshly prepared deep butyric solvent, which showing that the recovered deep butyric solvent maintains its integrity. Hence, the possibility of reusing the deep butyric solvent with a lithium bromide reaction media in the direct production of furfural from xylenes can reduce the potential economic impact on the process of the use of lithium bromide. In conclusion, first, the addition of metal halide salts to the acidic base deep butyric solvent was investigated as a strategy to increase furfural yield directly from xylenes. Second, lithium bromide allows the fastest and higher furfural yields. Third, the addition of halide salts is an easy way of increasing furfural yield by boosting the performance of pre-existing systems. Fourth, the maximum furfural yield obtained in the presence of lithium bromide under the optimized conditions was 89.5%. Fifth, the reaction media can be used at least 3 times without a major loss of yield. Lastly, the obtained furfural is of high purity and the recovered diptylic solvent maintains its integrity. So that's all from us. Thank you.